Okay, so far we've talked about Boyles and Charles, and our next gas law is called Gay-Lussac, and this is yet another Frenchman. And Gay-Lussac was also a hot air balloon specialist like Jacques Charles. But he looked at a little bit different of a relationship. He was looking at temperature and not volume, but temperature and pressure, which is a little different. And one thing to note here, if you are going to look at the effects of temperature and pressure, you have to have a fixed volume. All right, and the only way to have a fixed volume means you have to have a non-flexible container. A non-flexible container, so something that is rigid. All right, so not a hot air balloon, something more like an aerosol can. So this image down here in the bottom right, this is what happens to an aerosol can when you throw it in the fire. So on all those cans, there's giant warnings that say, do not put this container in a fire. It says warning, and it's not necessarily talking about that it's flammable. So the issue isn't so much that it's flammable. The warning specifically says contents under pressure, and therefore you can't put it in a fire. That would be bad. So what's going to happen when you increase the temperature on a set of particles when it's in a non-flexible container? Well, your temperature, increasing the temperature is going to make your particles go faster and have more energy. So if you are going faster and have more energy, how do those things relate to pressure? Well, going faster means that you are going to have collisions more often. And if you have particles that have more energy, that means you are going to have collisions that are harder. And what do these two things mean for pressure? Well, more collisions more often that are harder. These two things together mean that you also have an increase in pressure. So if you increase temperature, you will increase pressure. So that means these two things also have a direct relationship. So you're going to have a similar type graph. Pressure going up as temperature goes up. But again, this temperature must be in Kelvin. Okay, so do not ever be tempted to throw a non-flexible container into a fire because it will explode from the overwhelming amount of pressure in a can. You do not have to test that hypothesis on your own. You can just believe me. Okay, so what we have here, we've got our GIF here. So this is just showing the motion of particles at our two different temperatures. So if you are at a cooler temperature over here, you can see that these particles are moving a little slower. When they hit the sides of the container, they are not generating as much pressure. As opposed to this hot gas over here on the right, you've got those particles moving at a much faster rate, and since they are moving at a faster speed, they are hitting the wall more often than the container on the left, and they're also hitting at a harder force, so they've got a higher pressure. So the formula we are going to be working here, it looks very similar to Charles's law. All right, which should make sense. So it looks similar to Charles. And what you are going to notice, is that you still have temperature in the denominator. All right, so you still have temp in denominator in both of these laws. And that's important to remember because you can always remember temperature is in the denominator, period. So if we rewrite this as just a straight fraction, so it's P1 over T1 equals P2 over T2. So we just swatched out the volume in the numerators for pressures now. So just like in Boyle's law, pressure can be in any pressure unit. So again, we're going to see ATM, we're going to see millimeters of mercury, we're going to see kilopascals. Those are the most common ones that you're going to see. And it doesn't matter which of those you see as long as P1 and P2 are in the same pressure unit. But your temperatures are going to have to be in Kelvin. And again, so Kelvin is equal to degrees Celsius plus our magic number of 273. So we've got P1 and P2, and we've got T1 and T2. And we'll do the exact same thing here. So looking at P1, we need to clear out the T1 in the denominator. So we are going to multiply. So we're going to start off with that P2 over T2. But if we're multiplying both sides by T1, that puts that T1 in the numerator. Likewise, for P2, well, we've got P1 over T1 on the other side. And to move that T2 in the denominator over, we're going to have to do the inverse operation and multiply both sides by T2, so that gives me that. But let's go ahead and do the same trick for my temperatures, and let's cross multiply those up and rearrange and recognize that that's P1 T2 equals P2 T1, opposite numbers there. So that's a plain algebra 1 trick. You should recognize what that is. So if I'm trying to find T1, well, opposite of the equal sign, I have P1 T2. To move my P2 over, well, it's currently multiplied, so inverse operation would be to divide by that P2. For my T2, I've got P2 T1 on opposite side, and to clear out the P1, it's multiplied. Inverse operation is to divide, so that moves that there. If you need help rearranging these formulas, then you should really come and get some extra help from me on that. Okay, so here's our practice problem. So Zippy again. He's interested in a 255 milliliter vacuum packed can of Pringles in his hotel minibar. Okay, that's a volume. All right, so let's just mark that. That's a volume. Assume the chips were sealed at a pressure of 505 millimeters of mercury. That's a pressure. At a temperature of 5 degrees Celsius. That's a temperature. Okay, so as Zippy is examining the can of chips in his 19 degrees Celsius hotel room, that is a new temperature. So now I can label that as T2 and this 5 degrees as T1. What is the pressure inside the can now? So that's asking me for a pressure. That's asking me for a second pressure, which means this must be a first pressure. So let's look back at this volume. Do I need that piece of information? Is that a critical piece of information to solve this problem? No. And how do I know that? Because this does not change. At no point in the problem does it mention the volume changing. So if the volume's not changing, then this is extra information. And extra info we don't have to include in the problem. So I am looking for a P2. So what happened to my temperatures? Well, my temperature was at 5.0 and it went up to 19.0. So my temperature increased. So what should happen to my pressure? Well, they have a direct relationship. So if my temperature increased, my pressure should increase. So that's what I should expect in the problem. Now I am looking for P2. So from the previous page, what was my formula for that? Well, it was P1 over T1, and then I moved my T2 over, and it was like this. So I've got P1 times T2 divided by T1. So the first step I need to do is I need to take care of those temperatures. So T1 is equal to 5.0 plus 273, and that would be 278 Kelvin. And again, I'm dropping off the 0.0 because my sig fig says to the least number of decimals. T2 19.0 plus 273, and that's going to be 292 Kelvin. Same thing, no decimals because of the sig fig. All right, so let's plug my numbers in. So open parentheses, my pressure, 505 millimeters mercury, times T2, don't mess that up, 292 Kelvin, close parentheses, all divided by my T1, which was 278 Kelvin. So let's do a quick sig fig check here. 1, 2, 3, 1, 2, 3, 1, 2, 3. So I'm going to round my answer to 3 sig figs at the end. That's easy. Okay, so in my calculator, open a parentheses, 505 times 292, close parentheses, divide 278 equals, and I'm going to have to round that to 530 to show 3 significant figures. That's a decimal point there. Do not put a 0. If you put a 0, that would add another significant figure. What unit am I going to do? Millimeters of mercury. Now, does it matter that I'm using millimeters of mercury and not atmospheres? Absolutely not. Doesn't matter at all. Okay, so 530. What did that do? 530 is larger than 505, so my pressure did in fact increase, and my problem appears to be correct.